I'm opening up the webinar series for today, where we're covering the BPI Building Analyst Session 6 of our training series. And today we're going to be talking about combustion appliance safety testing, combustion appliance safety understanding, as well as lighting. This webinar series is brought to you by the Multifamily Upgrade Program, which is a PG&E whole building performance rebate program for retrofit multifamily buildings in PG&E service territory. Today you're going to be hearing from Scott Blunk, who is the Director of Operations at Partner Energy and a BPI proctor. As I said before, my name is Mike Maroney and I'm the Technical Manager for the Multifamily Upgrade Program. This webinar series is offered to you for free through the program and is one series of trainings that we're offering. A separate series of trainings is now complete and available on YouTube. Those are the EnergyPro technical webinars, and there was a series of 5 tech topics that we delivered. You can see on your screen here the topics covered the range of domestic hot water to cooling towers and chillers. All of those courses are available for on-demand viewing. The series of Building Analyst courses that we've been covering started in May, and today we're going to be finishing up the last bit of the technical training pieces related to this training series. The Building Analyst Assessment is going to be a training course which will kind of bring together all of the theoretical knowledge that Scott has been teaching over the past weeks into a practical application of how to analyze and assess a particular building for as a BPI building analyst. What's coming up after the August 5th, the last webinar training that we're offering, is we're going to be offering a full day of diagnostic testing available to anybody. This is going to be hosted on August 20th at the PG&E Training Center, which is in Stockton, California. This training center is complete with a variety of lab testing equipment. So these are kind of modified furnaces, forced air combustion appliances, domestic hot water systems that are open and available for testing. So Scott and some of Scott's colleagues are going to be hosting a training to give you some hands-on perspective on using the tools and getting your hands dirty with understanding how these pieces of equipment can be analyzed and assessed at the Stockton Energy Center, so be aware of that. The following day, on Friday, August 21st, there is an opportunity to take the written exam that is going to be hosted at the same place in the Stockton Energy Training Center. There is a fee required for the written exam, and if you would like more details, please email Kim, who is a colleague of Scott Blunk, Kim Hoskin at Partner Energy, and her email address is on the screen there. If you have trouble contacting her, please reach out to any one of us and we will make sure that you have the right information for taking the test. As a caveat, or as a piece of information for you all to be aware of, this BPI Building Analyst Training Series is a series of webinars that are organized in 1.5-hour chunks. When I first took a BPI Building Analyst training course, the course was 4 days of 8 hours in-class training with approximately maybe about 2.5 hours of my own time studying after the course. This is the kind of level of effort that you can expect to need in order to pass the BPI Building Analyst exam, written and especially the field exam portion. So while we're making this available to you as an introduction and as a way for you to get involved in BPI Building Analyst, we want to make sure that you're aware that there's an additional extensive amount of research and study that we recommend that you take to augment the training and the knowledge that Scott has been offering through these webinar series in order to prepare yourself for the written exam and for the field exam. So this Introduction to Building Analyst training gives you the overview of the theories, but to really understand the concepts behind the theories, we recommend that you do some additional study on your own time of the materials provided, as well as any other resources that you can get your hands on. And if you would like some recommendations of resources, we would be happy to point you in the right direction of that. So be aware that to prepare yourself for the exam, you should budget some of your own time for self-study. And with that, I will hand it over to Scott to give you any more context on the future training and exams that are going to be offered, as well as to get started on the topic and the concepts for today. So take it away, Scott.
Thank you, Mike. Yeah, I think you said everything that needs to be said. If there's questions, shoot them over. And this goes throughout the whole presentation. If there's any questions, you can ask a question via the questions box on the webinar screen, and Mike will answer it or get it to me, one of the two ways. But yeah, hope to see many of you excuse me, in Stockton for that in-person, since I haven't met any of you, for the in-person training and to get your certification. I think it's a
Hey, Scott, did we lose you? You might have muted yourself, or maybe we lost Scott briefly. While we're waiting for Scott to rejoin the call, there is a person on the call who has raised their hand. It's easier for us if you would type your question in chat. That's caused mostly by other people's having their lines unmuted and having issues related to feedback and things. So if you can chat your question, I'd be happy to answer it. Otherwise, we can open up the call, but we'll do that at the end of the call in order to offer you a chance to speak on the call. Scott, it looks like you're continuing to present, but I still can't hear you. So if anybody on the call can please give some feedback as to whether or not they can hear, that would be great. Okay, great. Yeah, so so it sounds like everybody's having the same issue. So Scott, if you can hear us, can you please log out and call back in? And while we're waiting for that to happen, I wanted to answer one of the questions that have come through in chat. You had mentioned that the YouTube videos, however, I tried to watch the videos for session 3 and 4 and they were not uploaded to the YouTube channel. Is there a reason for that? There is a reason for that, and I apologize. Those should have been uploaded to the YouTube channel, but it takes us some time to process and convert and upload the videos. I will check in on the status of that and make sure that those are uploaded as soon as possible. If you would like to reach out to me directly by email, I will respond to you and make sure that you're aware and notified when those finally do get updated. There's another question that came in. What is the name of your YouTube channel? The easiest way to get to the YouTube channel is just to search for in Google Multifamily Upgrade YouTube. I can provide a link to the YouTube channel page, and I will send that to everybody in chat now so that you have it available. I'll also give you some other contact points. So the program website is multifamilyupgrade.com, and if you go to the program website, you will find a link to the YouTube page. But I'm replying to everybody in chat for the link to the YouTube page now. If you pay for the $275 for the test and you fail, is there a retest fee? I am going to wait for Scott to get back on the call to answer that question, so stay tuned for that one. If there are any other questions in the interim while we're waiting for the audio issues to get resolved, please feel free to ask them by chat.
I am back, by the way, Mike.
Oh, great.
Sorry about that.
No problem.
Phone problem.
no problem.
So I just heard the end of that. Was there a question?
Okay, good. Yeah, there was a question. If a student pays for the test and they fail, is there another fee to retake the test? Or is there a fee to retake the test? So it's $275 for every time you take the test.
Yeah, essentially, yes. Because there's a flat fee from BPI no matter how many times you take the test.
Yeah, so as I understand it, that fee is mostly to basically buy the opportunity to take the test from BPI, not necessarily to pay you to host the test.
Right. So retest may be at a different rate, but yeah, it just depends on. But the majority of that money does go straight to BPI at this point.
Okay, great. Well, I think that's all the questions that we had in the interim, Scott. So why don't you take it away again?
Okay. All right. Sorry about that last time, everybody. So what I was saying was that the building analyst certification, the one that we're talking about now, is really the basis for BPI, and so it's the building block, it's the foundation, and what we're going to be talking about CADS is really the central point of the building analyst certification, understanding that, and that's what we're talking about today. If you're working in multifamily properties, getting the multifamily certification is great, but it doesn't certify you to do combustion testing. So, so this is really what you need. But combustion testing and passing the written test and the field test is great, and especially the field test is not that easy. You really need experience. Once you get certified, you really need some ride-alongs with somebody that knows what they're doing and can walk you through practical applications, because the field test is almost like a scripted dance. You have to do it a certain way, but when you get in the field, there's no script, and you've got to do it on your own, and you're going to do it a different way that suits the environment you're in. So anyway, we'll get going on combustion. So where does combustion occur? You know, combustion is just burning. Combustion occurs in your car when you turn it on, that's combustion. But in our house, it's typically going to be natural gas or oil or maybe coal, probably not dung. But all of that is a fuel source in combustion. So we're primarily concerned about gas, cooktops, ovens, furnaces, water heaters, and although we don't test it like the garages and the cars in it, we are still concerned about that getting into the environment, the living environment. So that picture there is of a wall furnace. That's the burner in a wall furnace. Just threw in a couple cool pictures. So combustion is nothing more than a chemical reaction, and it's down below. So you need fuel and you need oxygen. But with those two alone, you still need some sort of ignition source to get the chemical reaction started. And then once the chemical reaction is started, it produces its own heat, which keeps it burning. The fuel there is the CH4, that's methane, which is the principal component in natural gas. But it's not the only part in natural gas. So natural gas itself, it's colorless, tasteless, odorless. It's non-toxic. They add mercaptan, I don't know how to say it, to natural gas to give it an odor, but the true natural gas doesn't have that smell that you smell, but they give it the odor so that it can be detected. So what we call natural, yep.
It looks like the slides, we're still stuck on qualifications to perform CO testing.
That's bad. Okay, so.
And it looks like it's also in editing mode, so I'm not sure if it's updated.
Thank you. How's that? Yeah. Is that better?
So now we're looking at where combustion occurs and in presentation mode. So if you want to just go over that slide and probably the previous slide briefly again, that would be useful.
Okay. Oof.
Thanks.
Tons of technical difficulties today. I thought we were getting this thing down.
No problem. Thanks for fixing it.
Okay. So this was just talking about the certification and what's really required. But the building analyst is the foundation. This is the slide. This is the one I was telling you. This is the picture is of a wall furnace. And combustion occurs anytime a fuel is being burned. That is kind of the definition of combustion. And in homes, where typically it's the gas cooktops, the oven, the furnace, and the water heaters. There could be other space heaters, gas space heaters, or like wood space heaters, fireplaces. But typically it's the range, oven, cooktop, furnace, and the water heater. And this was the chemical reaction. That CH4 there is the methane. And so all the combustion is just a chemical reaction. You need a spark there on the left side to get the chemical reaction started, and once it gets started, the heat helps keep it burning as long as there's still oxygen and a fuel source. And then so this is where we were, where I was anyway, since you weren't here. Natural gas, colorless, tasteless, odorless, and it's non-toxic. They add a chemical in it to make it smell. Natural gas itself is much lighter than air, and it ignites at a temperature above 1,000 degrees, and you need at least 4 to 15% in the air volume to ignite. So that's why small leaks are not really dangerous, because they'll never get to the 4% of the volume of air to ignite. In a closed garage, you could build up slowly over time to that low level 4% that could ignite if you had 1,000 degrees, which could be your car or something starting up. So the natural gas, the chemical composition, it's primarily methane, but it also contains other anes, ethane, propane, and some other hydrocarbons, like there's sulfide and hydrogen. So that's a lot of these you see in after the combustion occurs. There's some sulfates in it, in the combustion byproducts and the exhaust that go into the air. But natural gas is not just methane. Okay, so the combustion triangle, what you need a fuel. Natural gas is primarily methane. You need heat, and you need oxygen. So the heat is the spark, and then once it starts burning, the heat is there anyway. Oxygen typically never goes away. And then the combustion triangle, out of that, from what goes in, what comes out is heat, water vapor, and carbon dioxide. This would be if there was perfect combustion. But oftentimes, combustion is not complete. But fuel, oxygen, and heat come in, and what should come out is water vapor, carbon dioxide, and heat. Carbon dioxide is not harmful. It makes you sleepy, but it will not kill you. But you often have these other combustion byproducts, which is excess air, but then there's also the trace compounds as a result of natural gas not being pure methane. Some of them are, the sulfur dioxides. You're going to get carbon, and you're going to get the carbon monoxide, which is what a lot of the combustion appliance safety is looking for, carbon monoxide, because it is a poisonous gas. Perfect combustion pretty much never exists. There's always going to be incomplete combustion. If you are testing an appliance like a water heater, and you're checking for CO, and the CO is 0, there's probably something wrong with your testing equipment. You should check it with another source. But the fact is, complete combustion pretty much never exists. You should always get at least 1 or 2 parts per million of carbon monoxide in it. That picture is of the bottom of a boiler. So that's through where you would light the pilot light. That's taking a look at the ignition underneath the boiler. All right, so quick summary. Most of the time, appliances are used to either heat air or heat water. I guess your oven is used to heat the turkey or something, right? But a lot of times you're heating either air or water. Fuel, oxygen, or heat are required for combustion to occur. And complete combustion creates very few byproducts, just water, heat, and carbon dioxide. And incomplete combustion happens almost all the time. You should never get complete combustion unless you're in a lab somewhere. All right, so a little bit more about combustion testing itself. So the level of CO in the exhaust gases really tells you a lot about how complete the combustion process is. So complete combustion would burn all of the fuel and give you low levels of carbon or no levels of carbon monoxide. So when you're testing and you have the lower the level of CO, the more complete the combustion is, and hence the higher the efficiency of the burn is. So high levels of CO is saying that the combustion is inefficient, and therefore the appliance is inefficient, or more or less efficient, I suppose. So high levels of COs, you just know you're losing efficiency, and it could be better. And when you measure CO, you're going to be doing it at steady state. CO, again, carbon monoxide. And CO is a pollutant. It's readily absorbed by the body and can impair oxygen carrying capacity of the blood. So basically, if you get too much carbon monoxide in your system, your blood stops carrying oxygen and you suffocate. CO detectors are required in California pretty much in every new home, and any time there's pretty much, anytime you're gonna sell the house, you're gonna do repair on the house, you would have to upgrade to make sure there's carbon monoxide detectors in the house. And kind of one little interesting fact about carbon monoxide, the molecule is so small that it can pass through unpainted drywall. So it's just another reason why paint that wall between the garage and the house, and it just helps keep out the carbon monoxide, reduce the pollution. So here's some concentration levels. So the concentration 35 ppm, that's parts per million. The symptom is headache and dizziness, and within 6 to 8 hours of exposure. So that's kind of long term. But most carbon monoxide detectors in the home are set at 70, so they wouldn't even pick up that level. And really, carbon monoxide poisoning, when we talk about it, what we hear on the news is people dying. But there's really, most of the time, if somebody's dying inside their home accidentally from carbon monoxide poisoning, it's because they've got their barbecue inside their living room or something. From just the furnace or the water heater, there's only a few deaths a year, probably less than 10. But we're still concerned about people having headaches, right? Or and just general malaise, just being sick. Just nobody likes to be sick. So there's more than just, the lower levels aren't going to kill you, but they're still going to make you sick. So just a reason we want it. Death doesn't really occur until you get really high levels. So the standards, this is the new BPI Building Analyst standard. This is the interim standard. There's the one in place now. This is the one, if you take the test in August, this is what you should be looking at and studying. These are the standards that they will use on the written test and the field test. I think it's good to look at the previous standards, but then starting January 1, there's another standard that's going to replace this one. But you can find this at bpi.org, and then look for current technical standards, and it'll walk you through where this one is. It's about 84 pages of delightful reading. All right, so just in summary, it's the incomplete combustion that's that creates the carbon monoxide, and you want to make sure you go through the BPI Building Analyst standards. Find that on their website. The equipment you will be using in combustion testing. This was a picture of my old case that I used to carry everything around in. In that, you can typically, that was about the size of a briefcase. You're going to have a manometer, typically a carbon monoxide tester or a monoxer or combustion gas analyzer. Those are all kind of the same words for the same thing. Something that's going to tell you the level of carbon monoxide in the exhaust gases. And then down there is also your personal CO monitor, one you're going to wear on your belt to make sure that you're safe. It'll give you an audible alarm if CO levels get high. You're going to need some drill bits and hole plugs, but not so much anymore. BPI's done away with the testing for draft. Smoke pins and mirrors are helpful to check for spillage. A flashlight helps oftentimes with checking for spillage. A stopwatch so that you can time. Well, it's going to be on your phone most of the time. Some high temperature caulk, RTV is always good. And then anything that you bring in to a house, you want to have the MSDS sheet on. So when I say anything, it's going to be basically anything you would leave there. So like the RTV, you could leave some RTV in the house, and you should be carrying the MSDS sheet. MSDS is Material Safety Data Sheet. So if the homeowner says, hey, what are you putting in my house, you can give them the sheet and say, this is what it is, this is, how bad is it for you, basically, kind of telling you concentrations of chemicals in it. Never had anybody ask me for those, but BPI requires you to carry them. Good practice, or just good thing to do. Your personal CO monitor we talked about, and usually just some other random hoses and hose connections are typically going to be helpful. So your combustion analyzer, this is the kind of the new style. This is what we're using these days when we go out in the field. This Bacharach, there's a lot of different manufacturers. This is kind of my favorite manufacturer of these. I just trust them. I've used them for so many years. But this will tell you a lot more than CO levels. I think it's about $750, so it's not cheap. But it'll tell you actual efficiency of the burn. It'll tell you oxygen content, CO2 content, temperature, in the exhaust gas temperature. It'll tell you ambient temperature. So it does a lot more than what you need. Typically, when you're just doing the BPI Building Analyst exam, but a lot of that information you'll use like at different parts of your career when you're out there testing. The inspection mirror, we'll talk about this in a little bit. When you test, you're going to be testing. One of the tests is for spillage. So that's, are the exhaust gases spilling out of the exhaust system and into the living environment? And there's really two ways to do that. You can do it with either smoke or mirrors. The mirror is a good indication that it's failing. smoke is a good indication if it's passing. So I've kind of went away from the smoke because it just requires an extra step of lighting the smoke stick or something, and just one more thing of carrying, where the mirror is just, you just put it up there and it's good. And what you're looking for is the spillage will spill out of the draft hood and onto the mirror and fog it up, just like breathing on it would. So if it's fogging on the mirror, you know that it's spilling. But you could also do that with a smoke stick if you chose to. And then you're going to also use a gas leak detector. This this is also a back rack model, the larger one, but the gas leak detector is very sensitive, incredibly sensitive, and will pick up minute gas leaks. So you have to be careful when you use it, because you will find a gas leak in every home you go into. And if you don't, give me a call. I'd love to know about it, because I've never found a house without any gas leaks at all. But a lot of it's the sensitivity you're going to be setting. Your gas sniffer is the other click wheel name for it. The gas sniffer, it depends on how sensitive you're going to set it. So it'll pick up just minute gas leaks. And the typical procedure is, if you find a gas leak, you should then be using a bubble solution to spray on where that gas leak was detected. And that will help you understand how big or small the gas leak actually is. And it helps you pinpoint where it's at. And then you can kind of make that decision on what to do with that gas leak, or what you should do. Your personal CO monitor. This is a really old style one. There's the new ones are kind of half the size of your cell phone in yellow, are the kind of the ones that I like using these days. But this is my old one. But you're going to be wearing that at all times during any testing in the house. Anytime you're in the house, you are to be wearing a CO monitor, personal CO monitor. And it should have an audible alarm that will go off at different levels of CO that you can set. Some are preset into it, but you must turn it on before you walk into the house, and monitor it while you're in the house, whether you're doing testing or work in the house. All right, so the combustion analyzer is really telling you, it is used to measure the level of CO in the exhaust, and how safe it is, how efficient the combustion is. You use a mirror when you're performing the spillage test. Gas leak detectors help you find gas leaks, and wear your personal CO monitor all the time. All right, so the testing and kind of the test order. I still have draft on this slide, but draft in the new BPI standards has gone away, so we don't do that test anymore. But so I've taken it out of some of these slides. So usually when you're doing combustion appliance safety testing, you're going to be first thing you're going to be checking ambient CO. Then you're going to be doing gas, and then worst case depressurization, spillage, and then an undiluted CO test. And during all of those, you're going to be checking your ambient CO. And we'll walk through each of these. Your ambient CO test. So at 35 parts per million, you should turn off the appliances, ventilate the house, and leave. But from what we saw before, 35 is really only, after, I think it was 6 to 8 hours of exposure, you'll get a headache. So it's not like don't run from the house screaming or anything, but you should turn off the appliances and try to be able to pinpoint where that source of combustion carbon monoxide is and get it fixed before you really go through all of the testing. And then the 24-hour exposure limit is 9 parts per million. So the ASHRAE standard is that, so essentially like if it's at 9 parts per million constantly, ASHRAE is saying that's okay. That's pretty high. Definitely tested houses that have a ambient CO. So ambient, the word ambient just kind of means the surrounding or the surrounding air. So it's not, you're not, ambient CO test is not testing any appliance. It's just kind of testing the air in the building. And on the field exam, when you talk about ambient CO testing, you should turn it on outside. You'll get your reading outside. Typically, it's going to be 0. Maybe if you live in LA by the 405 or something, it could read 4 or 5 or 6 parts per million, but probably not any higher than that. But you might get a few parts per million outside. But then, so you turn on outside and you take a look at it. Then you walk into the building and you walk, kind of slowly meander through the building, the house, and see if the readings change. And the reason you get the reading outside before you go in so that you can compare the two. And on the field exam, when you talk about this, make sure you're comparing the outside to the inside. And saying, well, outside is 0 and inside is 1 is not comparing the two, right? What you're saying, if outside is 0 and inside is 1, then there's a potential CO problem in the house. It's small, right? But you're picking up something that could be an issue. But if the outside is 1 and you walk into the house and it's 1, it's telling you that all it's doing is picking up the outside CO inside the house. So that there's really might not be anything at all going on in the house. And again, 1 is pretty small. That's almost measurement error on these. But if you were outside and got 0 and walked in and got 3 or 4, it should really be, light bulbs should go off in your head. Oh, there's something going on here. Maybe she just baked a turkey or something, but or he baked a turkey. But you want to figure out what that is while you're in there testing the house. All right, so gas line inspection. And of course you check gas lines just because for safety. It's not about efficiency, right? Although I guess gas leaks are pretty inefficient by nature. But you're checking, it's a fire and life safety issue. And so you're going to check all accessible lines. And so is a gas line in a crawl space accessible? Yes, it is accessible. In the attic, yes, it's accessible. If you can get to it, if a gas line runs inside, that's considered not accessible.
Hey, Scott, I think we lost you again. Are you still there? Yep, I'm getting a note from all of you that you also lost Scott by audio, so apologies for that. While we're waiting for Scott to join the call again, if there are any questions about combustion safety or about the program in general, I can try and answer those now. The other thing that I wanted to mention as we're waiting for Scott in relation to all this combustion safety stuff, the levels are important to understand to really get a handle on what is the potential impact of some of these issues. But the way that I was trained on this, on combustion safety testing and combustion safety levels in general, is the goal of any healthy home or healthy dwelling unit is zero, right? Even if the combustion safety appliance action levels say that below 35 parts per million, you're fine for a certain amount of time, or below 10 parts per million, you're fine for a certain amount of time. I always think about it as, what amount of time and what level of CO would I want to expose my sister or my mother or my father to live in, and really that number is zero. So keep that in mind as another perspective on all of this combustion safety testing. The way that I would recommend, or ideally my future home would have no opportunity for combustion appliances to exhaust, vent, or perform combustion in the living space, and that can be accomplished with careful attention to this level of detail, and also careful attention to the design and organization of where these combustion appliances are placed within the space. Sometimes you can't fix all the problems, but I think the smart BPI analyst, or the smart way of thinking about this is zero is really the only acceptable healthy number for ambient CO in the space, and that's really kind of perspective for you in communication with potential clients or potential homeowners. This is a complicated and tricky issue to get across, because in one way you're basically saying the home is unsafe, but we've done this testing now and we think it's partially safe, or we're recommending that you take these actions to improve the conditions of the space based on the testing that we've done. And I think there's an opportunity to explain to the homeowner from the perspective of their health and their family's health, that these tests are vital and important and necessary, and really you want to make sure that you're not constantly living in a space that has exposure to some of these toxins and chemicals. And yes, I did get a question while we were waiting here for Scott to return, that the effects of CO poisoning, are the effects of CO poisoning cumulative? And yes, they are. So there is a different exposure limit recommendation for one time or for kind of immediate inhalation of CO versus over an 8-hour period. So over an 8-hour period, I think it's OSHA sets the standard. The OSHA recommendation for the parts per million of CO over 8 hours is much lower than the one-time exposure limit. So that's telling you that over the course of a given day, or over the course of any amount of time, that exposure to that toxin will build up in your system, or in whomever is exposed to that, and we don't want that to be the case. And we frankly know how to make sure that isn't the case. So yes, we do want to avoid cumulative exposure to these toxins. Another thing that I wanted to mention while we're waiting for Scott to join the call again is that the combustion is that CO, or carbon monoxide, is also known as I forget the correct term, but it's something like a leader chemical, or a indicator chemical, or something like that. So carbon monoxide is a relatively straightforward chemical to test for, but is also used as a proxy, or as a auxiliary measure of other toxins in the space. So you can use carbon monoxide testing to assess the overall quality of the overall air quality within a space. Some other examples of chemicals that are kind of auxiliary, you can kind of have an auxiliary perspective on if you test for CO are things like nitrogen dioxide and sulfur dioxide and radon. These are all other indoor air pollutants that they have their own tests, and this is kind of getting outside the scope of this particular topic on today's discussion. But I did want to give you perspective that carbon monoxide testing gives you an overall perspective on how the concentration of the air in the home is affected by other impacts besides just normal human breathing, maybe some moisture buildup from showers or from watering plants in the home, and maybe some smells and off-gassing from cooking that's done in the home. So carbon monoxide is an important safety issue to be tested for, but it also leads to kind of auxiliary perspective on the general overall air quality within a space. There's another question that came through. Are all electrical buildings exempt from the requirement for a CO monitor? That is a great question. I thought that your question originally was, are exempt from combustion appliance safety testing? And the answer to that question would be definitely yes. Combustion appliance safety only applies to appliances that use natural gas or propane or some other combustible fuel to generate the heat. But I'm not sure about the CO monitor. That is a statewide California requirement, and I believe it was instituted or implemented by the fire code. And I would have to look into that. So if you'd like more detail about that, please email me directly, and I will be sure to follow up with you on that requirement. The reason that I'm hesitating, by the way, is I'm not sure that there's a way of confirming for the life of a building that a building would be electric only. For example, there is a theoretical possibility that the building could be retrofitted with gas, and then I'm not really sure when the trigger would be prompted for combustion for CO monitors. There's also, as Scott mentioned, the potential for kind of ambient buildup. If you're close to a freeway, you're going to have a slightly higher ambient carbon monoxide level than if you're in the middle of the forest, for example. So I'm not sure about that, and I can follow up with you if I learn more.
Hey, Mike.
Yes.
I called in on my cell phone.
Okay.
Seems like internet's down in this office today.
Okay.
So Kim was going to try to pull the presentation up, if you can make her the presenter, or if you have it readily accessible and you want to pull the presentation up and display, and then I'll talk through and you move the slides.
Sure. I have it up, so I can just I can do that, or I can hand it over to Kim. Is Kim ready to go with that, or?
If you can go ahead if you want. If
Okay.
you've got it up.
Yeah.
Sure. So I'm
Were there
going to
any
show...
questions? Okay. Were there any questions that I would like me to answer while we're here?
There was one. We got into a question about. Well, first of all, aren't the effects of CO poisoning cumulative? And I answered that yes, they are. There is a lower threshold for the 8-hour exposure threshold than for the one-time exposure threshold of carbon monoxide. But if you'd like to answer that with any more clarity, that would probably be useful.
I'm not sure. I'm not sure of the cumulative effects of CO as much as certainly the longer you're in a level of CO, the more poison gets into your bloodstream. So in that case, yes, it's cumulative over time. But if you get exposed to it today and then in 2 weeks later get exposed to it, I don't think that type is cumulative.
Okay. The next question, do you know, are all electric buildings exempt from the requirement for a CO monitor?
Yes, I'm pretty confident they are. yeah, I would default to yes, and I would argue with anyone, but I also heard your answer saying like it's good to have because of ambient CO from outside, or actually from your car coming into your house. So I would certainly recommend having one, but I don't think it's required by law.
And there's a question for kind of an oddly worded question, so I'm not sure if I'm getting the gist of it, but it was ditto for closed combustion appliances, water heater or fan coils. I think that you're saying ditto in terms of the requirement for combustion appliance safety testing is not applicable to water heaters or fan coils that are closed combustion appliances, so that is also true. And that was kind of, Scott, while you were getting back on the call, I went on a bit of a tangent about the real goal in my mind, or the way that I was kind of introduced to this topic, is you can understand that there are thresholds for the parts per million requirement for carbon monoxide, but really the goal is zero, right? You don't want your younger sister or your baby brother living in a place that's got 8 parts per million of CO at any point in time. So we have the tools to study, to evaluate this stuff, and we also have the equipment such as closed combustion appliances to provide us with the heat and water heat that we want without putting CO into the space. So yeah, if you want to comment on that, and there's a couple more questions that I'll bring up before we get back into the slides here.
Okay. Yeah, I mean, I would say the goal is certainly 0 parts per million in your living space. And one way of doing that, or 2 ways of doing that, would be all electric appliances, and then closed combustion appliances. Closed combustion appliance, there is still combustion testing required on them, but it's pretty minimal because there's much less to test on them. But ideally, if you're going to have a gas appliance in the house, you really want closed combustion, and I think the goal should be getting rid of open combustion appliances in all homes. I don't know how you do that with the oven and range, but at least the furnace and water heater for sure. Okay.
So to build on that question, for closed combustion water heaters and fan coils, do we need to do combustion safety testing?
Yeah, we'll get into that in a little bit. You're still going to do some, but it's very quick and easy. But we'll get to that.
And then to close the loop on the CO detector in all electric homes or in homes that don't have combustion appliances, there's one comment that even an electric range or oven can produce CO from burned foods, so it may be useful in that scenario.
Yep, that's a good point.
The CO detector is required for house fires combustion. So it sounds like we're getting some feedback that the CO monitor is useful required, even in the all-electric scenario.
Mm-hmm.
And last comment is there is a cumulative CO, an effect from cumulative CO exposure, and it's primarily a neurological impact. But again, as Scott said, the goal of healthy living, I think, and we think through studying this stuff, that get rid of open combustion appliances and sources within the living space will go a long way to reducing the exposure of some of that stuff.
Yep.
So I'll turn it back over to you, Scott. We're looking right now at combustion appliance safety gas line inspection slide, and feel free to comment on any of those topics or get back into the slides from here, and I'll just move along when it's appropriate, or you can tell me.
Okay, I'll tell you. Yeah, that'd be great. So yeah, this slide, I don't know where it got cut off, but so this is just gas leak testing. You need to test all accessible lines. Accessible lines just means any line that you can get to. If it's in the attic or crawl space, that's still accessible, most likely. There are accessibility guidelines, but if it's running down a wall behind drywall, that would be considered inaccessible. So when you're going out in the field to do an actual test, you want to test every line. And a little primer on that: when you test, you're going to run your gas leak detector along the line, along the axis of the pipe at a speed of 1 inch per second, which is much slower than you think. So make sure you're going pretty slow when you do the testing, and then around each fitting and joint, you'll go 360 degrees around each of those. And that's also the kind of a speed of 1 inch per second. So the bubble solution is used to validate gas leaks, and the picture there is just showing a bubble solution. Actually it's Windex, it's not actual bubble solution, but on a leak that was found on a wall furnace. Yeah, so we can go slide 34.
Yep.
Okay, so worst case depressurization. In this test, the goal is to configure the house in the most depressurized state possible. And with that goal, and once you get the house in the most depressurized state, then you want to turn on all the combustion appliances. You're going to do it one by one, and then make sure that the exhaust system is powerful enough to counteract the effects of this depressurization that you created. And we'll talk a little bit about how to create that depressurization on the next slide. But a water heater could work perfectly fine under normal circumstances, but then once you get the house in worst case depressurization, maybe the vent stops working and it draws all the combustion gases inside the house. So we can go to the next slide. And in this slide, so it's just kind of a mock house, and what you're seeing is the different rooms. So the green arrows are showing the furnace supply vents into the rooms, and the red arrow is the return grill. And if you hit like slide forward button once, so what that's showing now is the master bedroom should have a plus sign on it. So the master bedroom, the walls are continuous there, showing that the door is shut. So once the house, the air handler is on, the supply registers are taking air out of the main house and dumping it into the master bedroom, which creates a positive pressure in that master bedroom. And it's because the pressure is higher in the bedroom than it is outside the bedroom, now it's just forcing the air inside the master bedroom out. So what that's doing is you've got a positive pressure in the master bedroom, and at the same time you're creating a negative pressure in the area where the whole house return in the hallway is. So the living room, everything else is going to be slightly negative. If you arrow to go advance again, that's just kind of what it's showing. The utility room now is negative from the doors being shut. The kitchen is negative. The living room is negative. The bathroom is positive for the same reason. And the bedroom is positive. So this is just using the central forced air system. But you also, when you're doing worst case depressurization, you're going to have like bathroom fans. There's probably a fan in the bathroom, kitchen, and utility room that's also going to exhaust gases out. So now, once you so start with the bathroom. You turn the bathroom exhaust fan on. It's going to be pushing more exhaust out. And now, the bathroom, depending on how much air is coming in through the HVAC versus how much air is leaving via way of the bathroom fan, the bathroom could be positively pressurized or it could be negatively pressurized. You don't know until you turn the fan on, and then you would check the pressure in that room. So if the goal is to get the negative pressure more negative, let's say the water heaters in the kitchen. So the goal of worst case depressurization then is to get the kitchen as negative as possible. So once you turn the bathroom fan on, the bathroom, let's say it becomes negative, then you would want to open the door between the bathroom and the hallway. And so that some of that negative pressure goes into the living room, kitchen, utility room area and creates even more negative pressure in that. So you would do that with every door in the house to get to the point where you find the most negatively pressurized state where the combustion appliances, each combustion appliance resides. So it's pretty simple testing. Dealing with pressures, since you can't see them or feel them, is a little tricky, but you'll get that in the field. It'll become more clear. And go on to slide 36 now. So you're going to do the spillage test after you get the house in worst case depressurization. And the spillage test is just that. Just see if the gas is spilling out of the exhaust pipe at the draft hood, is spilling out into the space, the living space. So a lot of times under worst case depressure, it could be fine under natural conditions. That's when the worst case depressurization doesn't exist. But under worst case it fails. So only if it fails under worst case would you then test under natural conditions. So the spillage test, going on to slide 37. The spillage test must be completed for all natural draft space and water heating systems. I would say really you're going to try to do some form of a spillage test on any combustion appliance. Induced draft systems, though, there's no gap in the exhaust system to really check for spillage. So it's a little more ambiguous of where to test. But any spillage after 60 seconds from the startup is considered a fail. So it's okay when you first turn it on if it's spilling, and it's okay at second 59, but at second 60, it needs to be passing. And well, a couple slides down. So we're on slide 38 now. So spillage is just the exhaust gases spilling out of the flue and into the living space, as we said. And there's what's called a cold air plug. When you turn on a water heater for the first time for the day, the vent pipe is cold, or at least room temperature, right? And draft works best when the exhaust pipe is warm. So it just helps the draft. So that's why we give it the 60 seconds, because sometimes that 60 seconds, it needs that to heat up the exhaust system, and then it'll start drafting. So under worst case or natural, failing for 60 seconds is okay when you've got a cold exhaust system. But spillage is also caused by other things, improper venting, obstructions, improper common vented appliances. I'll show you some of that. A lot of times when I see an appliance that is that is spilling, it's because the vent system is run incorrectly. Like there's too many elbows that obstruct the flow, or the principle of a natural draft appliance is that hot air rises. So if somebody plumbed the vent pipe going downhill, that's going to stop the hot air from leaving. So a lot of times that's going to cause a spill. I've also found bits of insulation kind of stuck inside the vent pipe and obstructing it. So all those are possible. So this is a picture of somebody doing a spillage test on a wall furnace. He's using smoke there, but you can see how the smoke is being drawn straight into that draft hood on the wall furnace. So if the smoke was not being drawn into there, but was kind of meandering around the outside or being blown the opposite direction, it would be a fail. And again, so when you check using smoke, you're going to have your smoke stick, just as this picture shows, right on the edge of the draft hood. This is the top of a water heater. And so that you kind of are giving the smoke a choice to be sucked up the exhaust or not. So this one is passing. The smoke is being drawn straight into the vent hood. If the smoke is, again, kind of turbulent and or blowing out, it's going to be a fail. So spillage tests, I've quit doing smoke. I always use a mirror these days because it's just more convenient. But so you would hold the mirror kind of the same point where the tip of that smoke pin is, and with your flashlight on the mirror, you'll see if it fogs up, that means it's spilling. So it's a pretty easy test. And then when you're part of your combustion appliance safety testing is checking for vents, checking the vent system. So you want at least a 1/4 inch rise in the vent pipe for every 1 foot run. So basically, just make sure the vent is continuously going up everywhere. That's probably one of the most common causes of vent failure. You want to see at least 3 screws holding the connections together. If it's a single wall, double wall, you don't need fasteners. Or at the draft hood, you're going to want to see some fasteners, some mechanical fasteners. You want 1 inch clearance from combustible materials where the flue penetrates the building assemblies. Well, really from any combustible material. So the 1 inch clearance is the requirement for B-vent. B-vent is a double wall venting system as opposed to a single wall, which requires more clearance. I've debated with many building departments whether drywall is combustible material. It's quite clear in the building code that drywall is not a combustible material. Well, at least it's quite clear on one page, and on another page of the building standards, it's quite clear that it's not, or that it is combustible. So it can be argued either way. I typically lose, and it's typically considered combustible. And one of the best tests for a vent system is just to grab it and shake it. Just do a light shake if it's cold. Make sure that it's sturdy and kind of doesn't fall apart in your hands. Go on to slide 42. The last test, and this order is just the order that I found that makes the most sense. But you're going to check for undiluted CO. So what you're doing is, as opposed to ambient, that's certainly diluted. This is undiluted CO. So you're checking the carbon monoxide levels in the exhaust gases themselves. There'll be some pictures coming up. But you want to get your probe down inside the exhaust before the draft hood to see what the level of CO is. And again, it tells you about the efficiency of the combustion process and also the potential danger of the appliance. Because kind of the question at the bottom there, does it matter what the CO level is if the appliance is venting properly? And it does for efficiency. For safety, if the appliance is venting properly, CO levels may not appear to be an issue in the exhaust because it's completely leaving the building. But if things change and the vent a bird builds a nest on top or something, now it's going to be venting into the house and it's going to cause a problem. So yeah, even if the venting system is working properly, we want to make sure the CO levels are safe. Page 40 or slide 43. We are. Slide 43 shows a natural draft water heater. And this kind of shows where you're going to do each test. The draft test is no longer in the new standards, so the draft test you'll just skip. But this is a natural draft water heater. So you're going to do a spillage test right at the vent hood, right at the very top lip of that, and then you're going to do a CO test down inside, and that's a picture of me actually doing this test, and I've got my probe. You want at least 2 to 3 inches down inside the exhaust before the draft hood. So I've got a hook-shaped tube that's going down inside a few inches. And that's measuring CO. The next slide on page 44, or slide 44, shows you 3 different configurations of water heaters. They're all about the same. The one on the far left is essentially just has an elbow. It looks like there's still a draft hood there. So it's going to be just like the one we just saw, or the one in the middle. They're both really the same configuration. The draft test you're not going to do. The one on the far right is a power vented water heater. And so this is, you're going to test, you're not going to drill anything here to test for CO. Spillage is really, you're checking for tight connections. Where you're going to check CO on that water heater is where it terminates the building. So wherever you can get to the other end of the exhaust pipe, that's where you're going to want to test it, as long as it's safe to get there. Next slide, 45. So an undiluted CO test. This is, you're not going to find something like this in most homes. This is a smaller boiler. You could if they've got like hydronic heating in the floor or something, but it's just a water heater without storage. So you're going to check the spillage at the draft hood again. That thing about 1.5 feet, 2 feet up is the draft hood. You're going to check spillage there. And you're also going to check for CO, kind of get up under the hood and back down in there to check for undiluted CO. And then, of course, on all these, you're going to still be checking for gas leak testing. So on this one, oh, I can't use my pointer, but there's the gas pipe on the left. There's the green handle on the gas shutoff. You're going to check that pipe all the way down, and as much as you can get to until it enters into the water heater or the appliance, probably a boiler. All right, so going on to slide 46. So this is a natural draft furnace. And so again, spillage, you're gonna check at the top or the very bottom of the top green piece. So if there's going to be spillage, it's going to be coming down out from kind of inside and spilling up over the lip. And for CO testing, this is a furnace. So if you remember what the heat exchangers look like from last week, you're going to get your probe up inside there and go into each heat exchanger, because the heat exchanger is going to end there, and then it's going to be open to the air, and the exhaust should go straight up out the exhaust pipe. So you're going to want to check for the CO before it gets into the open air. Much easier if you see this in person. And we will in Stockton in a few weeks or a month, maybe. So again, this is an induced draft model furnace. You're typically going to drill a hole in the vent to check for CO here. New standards, there are other ways to check for CO, and we'll talk about those when we get into the field. But spillage is kind of one of those pretty hard ones to test for here because there's no open air gap. A lot of people talk about kind of checking right there where the vent pipe connects to the furnace itself. I've never found a leak there, but you could do your spillage test there. Next slide shows a closed combustion high efficiency furnace. And so here you're not going to be doing as much testing. You're still going to be checking for gas leaks, of course. There's no possibility of a spillage test here, so there's nothing to test for. And then you'll still test for CO in where the exhaust exits the house, and that's that picture on the right. One's an air intake, one's an air exhaust. So you'll check it. Check the undiluted CO where it exits the house. Same thing, get your probe down inside 2 to 3 inches. For me, at Partner Energy, I don't have any of my guys test this if it exhausts on the roof. We just don't get on the roofs. Too much liability. So a lot of times you've got this, or same thing if it's a sealed combustion. condensing water heater. You're going to check the line, and you're going to check where the exhaust exits the building, if it's accessible. The next slide, 48, shows a very large package unit. This is on a commercial building, but it all applies to residential package units. So here, most of the standards, something like this, where it's completely outside the building envelope, the only testing you would do would be gas leak testing. There's no spillage test possible. The CO comes out of that little silver hood there on the side of the unit. So you could check for CO if this unit's accessible, and it's still a valid test, right? You're still, even though it's not going to poison anyone, it's still telling you how efficient the appliance is working. But in general, a package unit that's accessible, you're only going to check the gas for gas leak testing. And inside the unit, you can turn it on and you can check. You're going to be turning on and monitoring your ambient CO, but you could also stick the probe up into a supply register, and that could tell you if there's a cracked heat exchanger, but it's not required to do that test. All right, slide 49 or 50. So what this shows is a commonly vented appliance. So that's where two appliances, here you got a furnace on the right and a water heater on the left. The exhausts come up and merge together, and then they vent out of the house in one common vent. It's pretty uncommon to find a commonly vented setup like this. Very few of them exist just because they're not, they don't exist because of the safety factor. You turn one on, the exhaust gases could be coming out the other one, where here it shows the gas furnace, when it's on, it's exhausting into that same room because the water heater is just an open pipe, right? So it can force the exhaust gases out that direction. They can work properly too, but they're just more complex and they're more dangerous. So you want to avoid this setup if you can. You don't want to install this for sure, but if you find it, how you're going to test it, it's all the same, except that you're going to test the appliance with the smaller BTUs first, which is typically the water heater. You're going to test that one, and then you're going to turn on the furnace. And you need to do the testing on both of those with each one on by itself, and then each one running at the same time. So there's a few different combinations here that you'll want to test under. The next slide, 51, shows these are the new CO thresholds for BPI. These are not the CO thresholds for the PG&E program right now, if you're in this program. But these are the new BPI standards that are coming into full force on January 1. These are quite a bit higher than what we've seen in the past in general. So it's just going to be something to get used to. Going on to slide 52 shows oven CO testing. So most ovens are going to have something like what you find here, where if you've got a gas oven, the gas is burning underneath a big flat plate, the bottom plate of the oven, the gas is on. It comes up and it circulates around, cooks your turkey, and then it comes up out of an exhaust pipe and it terminates where these probes are going in. And then that exhaust gas just dumps into the room. Now, ideally, you're going to have the vent fan on above this range, and ideally that's going to be venting outside the house, because ovens typically produce the highest level of CO of any of the appliances in the house. So you're going to test the ovens in that manner. Where that exhaust leaves the oven, like I said, it's typically right there in the back plate. If you squat down on a lot of these, you can see in there the pipe exiting. So you have to get down and kind of look. But
But typically it doesn't cover that whole space. So you see in the picture on the left where he's testing, a lot of times it's right in the center where the exhaust comes out. But if you stuck your probe on the far right or far left, you would not get a reading, because where the exhaust actually comes out is usually only about 4 inches wide, right in the middle. But also that's not the only place you find the exhaust terminating on ovens. It could be on the top of it itself, different places on different ovens, but that's the standard place. And of course, before you do CO testing on an oven, sounds silly, but you want to check the oven and make sure that last night's dinner is still not sitting in there. People like to store everything in their ovens, from guns to Tupperware, and you don't want to turn it on when things are inside, because you don't want to be buying Tupperware for somebody or burning their house down. So before you turn the oven on, make sure you check inside, what's inside. We have bought a oven for somebody before, because he didn't check. The guy out in the field didn't check, and there was a cutting board inside that caught on fire. And for BPI, there's no standard procedure for testing CO on the burners on the top. And there can be, depending on what program you work in, but for BPI there is not. So we're getting pretty close to the end, and we're not there. Let's see, a couple slides. I'll finish this section, and we'll turn Mike back on and see what he'd like to do. So, so your combustion appliance testing, you would do this at test in. Ideally, you're going to do a test in, then you're going to retrofit the house and make it super energy efficient, and you're going to do a test out to make sure what you didn't cause any problems. And you should really be testing along the way while you're working in the house, but make sure you use that first test, to create a scope of work for the house that incorporates the fixes. So that seems obvious, but make sure you don't use up all their money putting in granite countertops or something, and then don't fix the gas leaks. Next slide, 54, is the summary. Make sure you're continuously monitoring ambient CO while you're in the building. Test gas lines on all exposed gas lines. Set the building a worst case, and then check for spillage. And then you're going to check for CO, combustion, carbon monoxide, and exhaust gases. And with that, we are to electrical, which is slide 55, but we're also out of time. So, Mike, what do you propose we do?
Let's offer it up.
There's 15 slides, 16
to the audience. So. Why don't we do this, Scott? Why don't we continue on with the electrical basics? Anybody who has budgeted only time through 1:30 can feel free to go tend to your other needs. We will continue doing the presentation until it's complete, and all of this is being recorded and will be uploaded to our YouTube page later. So please stay with us if you want to interact with the presentation. If you have to leave, no problem. We will upload this presentation along with all of our others to our YouTube page, and you can view it on demand there.
Great. Thanks, Mike.
Yep.
That sounds
perfect.
Great.
Okay.
All right. So there's only a couple slides here, and I cut out about 80 slides probably from this presentation, what I would normally give, to try to just hit the few basics that BPI is concerned about on building Analyst. And so there's only basically light bulbs and a GFCI on here. So this is a GFCI outlet. I'm sure you've all seen them at this point, GFCI, ground fault circuit interrupter. guards against electrical shock. If there's ever a slight difference in the current going from the left side to the right side of the plug, it will sense it and it'll shut off the switch, because the current should flow in through the hot, the smaller side, and then out through the neutral side. So your electricity coming in isn't technically consumed necessarily. It kind of flows in and flows out, and it senses it, and it'll trip if there's a variation. Now, what this picture is also showing, slide 56, I'm sure Mike's there. What this picture is also showing is what you typically find if you take the cover of the electrical outlet off. So if you're in the field, grab your caulk gun and seal up at least between the box and the drywall. That'll reduce air leakage into the house. Now there's holes in the back of the box where the wires come in and out. You can't really fix those, but it's kind of like closing a window halfway, right? You're at least stopping some of the airflow. So you do what you can. Can't get it all, but I would recommend at least sealing the box to the drywall. You can always put a plate cover gasket on, but typically it's very expensive if you're paying somebody to do that stuff. But if you do find the GFCI, you want to test it, best way to test it would just be with the GFCI plug tester as shown there. You're going to plug it in, you're going to see the two lights, you're going to hit the black button on the top. It should trip the outlet, and then so it'll shut off all the power when it trips. And then and you should be good to go. Then you just reset the plug and you know that plug works properly. And another use for your infrared camera is to find overloaded circuits. So this is taking a picture of a electrical panel. And what it's showing is those circuits down in the bottom left are overloaded or have the highest loading on them, at least. Maybe they're not overloaded, but there's a lot more current going through those. So it's just the infrared picture of your electrical panel can show you overloaded circuits. That's really all that's saying. So going on to slide 59, and lighting basics. And slide 60, if the efficiency of lighting in the industry is called efficacy. So when you talk lighting, you don't want to talk about how efficient a light bulb is. You want to talk about the light's efficacy. And it's a measurement of basically the efficacy. It says for the amount of electricity it consumes, how many lumens does it give off? And lumens is a measure of light. So efficacy is producing the desired effect. So light, obviously, the desired effect of a light bulb is to light up the house, not to heat the house. So efficacy is a measure of how well it does that. Slide 61. So a lamp is what you would commonly call the light bulb. In the industry, a homeowner would call it a bulb. You should call it a lamp. And then there's also the fixture, and the fixture is what the lamp or the bulb goes in. But a lot of times it's just called a lamp. And then all the lamps or the bulbs are rated in lumens. It's kind of how much light output they produce. Let's go on to slide 62. And that's just kind of the intro for the lighting types. Like I said, this is going to be pretty quick. Incandescent bulbs on slide 63. This is kind of goes back to the very beginning of the first light bulb. If you've ever seen some of those documentaries or something where Edison created the light bulb, it's going to look a lot like this. And maybe that's just a historical dramatization, but it's rolling up a little thin wire that's going to shoot electricity through it, and it lights up. It produces light, right? That's what you want. But light bulbs are actually much more efficient heaters than they are efficient light sources. But they are the cheapest, and builders especially want to put them in because they're cheap. It's a very low first cost. And you know all about them. So in a fluorescent, slide 64, the picture on the right is showing a screw-in CFL, compact fluorescent, the pigtails. You've probably all seen those by now too. This is a direct replacement for the incandescent bulb in the previous slide. The electronic ballast that is shown there, that's just kind of what it takes to get the light lit. Requires that circuitry in there. But the CFL is about 4 times more efficient than an incandescent bulb, a standard bulb. And that used to be one of the questions on the BPI exam is like basically, if there's a 100-watt light bulb and you're going to replace it with a CFL, what wattage bulb would you replace it with? And so essentially, if it's a 100-watt bulb, you're going to replace it with 25-watt bulb, roughly 25. The choices A, B, C, and D are usually, 23 is actually the correct answer, but that's roughly, so A, B, C, and D, if one of those is 23 is what you're going to go with. That's roughly 4 times more efficient. And then there's just electrical current that's going through the mercury gas that creates the light. And yes, the mercury gas and all those electronic components, it is a hazardous product, so dispose of it properly. And then there's LEDs on slide 65. This is the newest technology out there for lighting. The promise is it's going to be 4 times more efficient than the CFL, so 1/16 of the energy of an incandescent. I haven't seen that efficient of bulbs come out and be on the shelf yet, but most of the bulbs out on the shelf are about the same efficiency of a CFL. So money for money, I would buy CFLs, even though I have LEDs in my house, some of them. But LEDs are the most expensive to buy up front, but they're the cheapest to operate long term. They produce very little heat. That's because they're very efficient at producing light. They don't waste a bunch of electricity producing heat. And there's just how it works is just the electrons move in a semiconductor that creates light. And the lifespan, incandescents can last a couple years. CFLs, 5 to 10 years. LEDs, they say, can last up to 50 years. I'll get back to you on the field test on that one, but that's what they say. So my example, I kind of already gave you this. If there's 6 can lights with 100-watt incandescents, what's the proper CFL replacement? It would be 6 23-watt CFLs. 23 watts is just kind of the standard, but it's roughly 1/4 of the power of an incandescent. And in savings opportunities, I think this is dramatic because most people, including myself, don't want to get rid of their incandescent light bulbs because they're still working, and you think, well, I'll replace it when it burns out. But this calculation just shows you need to do it now and stop procrastinating, because the example here, 6 can lights, 100-watt incandescent bulbs in a kitchen. Let's say the lights are on roughly 4 hours a day. That could be more, could be less, but let's just say a 4-hour average per day. And then that's the math that shows you how many watt hours converted to kilowatt hours, and then multiplied by the price of electricity. That's at 15 cents per kilowatt hour, which is, my average kilowatts is 18. Average on my bill, right? The lowest cost first tier might be less than that, but anyway, this calculation used 15 cents. So those 6 bulbs in the kitchen are going to cost you $131 to operate for the year. If you switch them all out to CFLs, it would cost you $30 per year. So you'd save $100 in 1 year just replacing 6 lights in your kitchen. It's pretty dramatic. The problem is you switch them out and you're not going to notice a huge drop in your next bill because your bills fluctuate so much. But this is the math that doesn't lie. So just looking on Amazon and pricing those out, your 6 CFLs are going to cost you $13.43. Your return on investment is 1.6 months. So cough over the $13, put them in your house or your client's house. Do this math for them. It's pretty dramatic. In 1.6, they're going to be months. They're going to be making money. Easiest thing you can do: screwing in a light bulb, right? And in lifespan, we talked a little bit about this, but LEDs have incredible lifespans compared to incandescents, and CFLs are in the middle. And that's it. We've made it through all the technical difficulties today, and we'll open it up to any questions if you've made it through all of this.
Great. Thanks, Scott, and thanks everybody for staying on the line and working through the technical difficulties with us. Haven't gotten any questions since we went into the electrical and lighting section of the slides. So I guess just in wrap up here, I want to let you know that this presentation, along with all the other presentations, are going to be uploaded to our YouTube page or have already been, so please take a look there. The program that is sponsoring this training series is the Multifamily Upgrade Program, which is a whole building performance retrofit program in PG&E territory. If you would like more information about the program, please contact me. My contact information is on the bottom half of the slide that we're looking at. If you'd like any information about Partner Energy conducting assessments for your property, or Partner Energy providing additional resources for your BPI training, or to sign up for the the written exam portion of this training series, please contact Scott Blunk, and his contact information is posted on the top half of the slide here. One other question that came in as I was wrapping up is, why is there no more draft check? I think that's a question related to the draft test for you, Scott. So the last thing that I wanted to say is just thank you, Scott, for all this good information, and thank you for the resources and the detailed overview of the Building Analyst series over the course of these webinars we've been given. That's the last piece that I'll say for today, so I'll hand it over to you to clarify first about why is there no more draft testing, and then you can close out the session with the last word, and I will be ending in just a few minutes. So if you can answer that question, Scott, and then close it out, that would be great.
Okay, will do. Thanks, Mike. Thanks, everybody, for hanging on through all the difficulties today. Why are we not doing a draft test? I don't know. That just came down through BPI. I didn't see where they explained why that was happening or not happening in the future, but it is going away. The new standards, if you haven't read them yet, I would encourage you to do so. There's a lot of changes in them, and so it'll be a sea change coming up in January when they go through these new standards. So I would look through them, and it's a great question. I would encourage you to contact BPI and ask why that is going away, but it is. And so thank you very much. Sorry I couldn't give you a better answer on that. Thank you very much for being on the line today, and we will hopefully hear from you at the next webinar. Thank you.